Okay, and then recall the remainder value and also the error value of the series by using the integral test. We assume that the series terms are all positive and will eventually be decreasing. And we derive the integral test by using the fact that the series could be thought of an estimation of the area under the curve of a f of x function, and also f of n equals to an. Okay? And then we can do something similar with the remainder. And the first, let's recall the remainder. I mean that let's write the remainder value. And the Rn equals I starts from n plus 1 to the infinity ai, and it equals to an plus 1 plus an plus 2 plus an plus 3 plus it goes. Now if we start at x equals to n plus 1, take rectangles of width 1 and use the left endpoints as the height of the rectangle, we can estimate the area under the f of x, and that means the f of x equals to f of n, which is an. Okay, so that now we can take the f of x functions on the interval n plus 1 comma infinity. Okay, so the sketching will be like that. Okay, and the width will be 1, and the left endpoint will be valid. Okay. N plus 1, n plus 2, n plus 3, n plus 4, and n plus 5. Okay, and the colored, these are the green shaded rectangles. We can see that the remainder Rn is exactly this area estimation, and it will overestimate the exact area, and I mean that our Rn will be larger than or equal to integral from n plus 1 to the infinity f of x dx. Next, we could also estimate the area by starting at x equals to n, taking rectangles of width 1, and again then using the right endpoint as the height of the rectangle. This will give us an estimation of the area under the f of x on the interval n comma infinity. Okay, so that if we now take the x equals to n, okay, so that the f of x on the n comma infinity, and we will take the right endpoint, okay, here as left endpoint, as you see, okay, and then as you see these are the left endpoints of the rectangles, and now we'll take the right endpoint, so the graphic will be approximately like that. Undo. And this value is n plus 1, n plus 2, n plus 3, n plus 4, and it goes on. And also this is the yellow shaded area for the Rn, and now our remainder will be less than or equal to, okay, and the integral n to the infinity f of x dx. Okay, and we have just two different estimation for the remainder, okay, and let's combine them together so that we will find the n plus 1 to the infinity f of x dx less than or equal to Rn less than or equal to integration from n to the infinity f of x dx. So provided we can do these integrals, we can get both an upper and lower bound on the remainder, and this will in turn give us an upper bound and a lower bound on just how good the partial sum Sn is an estimation of the actual value of the series. Okay, I mean that let's get a better estimate for the actual value for the series as well. And first we will start with the fact that, my friends, S equals to Sn plus Rn, it was, right? And after that, if we use I will call this in the second inequality, and this is the third inequality. And let's use the second inequality. And after that, S equals to Sn plus Rn, which is larger than Sn plus integration from n plus 1 to the infinity f of x dx. If we use third inequality, and this will be now less than or equal to integration from n to the infinity dx. And putting these two together gives us and that putting these two ones together, it will give us totally Sn plus integration from n plus 1 to the infinity f of x dx, okay, less than or equal to s less than or equal to Sn plus integration n to the infinity f of x dx. This is the, maybe we can call the fourth inequality. This gives an upper and lower bound on the actual value of the series. We could then use an estimate of the actual value of the series, the average of the upper and lower bound. Let's work an example to understand this upper and lower bound of the summation, okay, exactly and clearly also. Let's pass to the other page. Example. Using n equals to 15 to estimate the value of one over n square and starts from 1 to the infinity. My friends, first, for comparison purposes, we'll note that the actual value of the series, okay, is known to be, and I mean that because of this is the comparison, okay, so that we know that the n equals to 1 to the infinity 1 over n square, it equals to pi square over 6, okay, and which is equal to 1.644934069. It goes on, it's irrational numbers, but now we will try to get the partial sum, okay, so when using the n equals to 15, okay, this is given, okay, right, and using n equals to 15, okay, so that the n starts from 1 to the infinity 1 over n squared, not infinity, it's 15, I'm sorry, so that okay, maybe it can be computed as the partial sums, okay, it's clearly, okay, so that the S15 equals to I starts from 1 to the 15, 1 over I square is equal to 1 plus, okay, and the 1 over 4 plus 1 over 9 plus, it goes on like that, and the 1 over 225, okay, and they compute this summation, you will obtain 1.580440283. That's the first 10 terms of the summation, or the 9 terms of the summation, whatever. And this is close to the actual value, as you see, okay? And in some sense, but there isn't really all that close either. Now let's compute the integrals. These are fairly simple integrals, so we will leave it you to verify the values, okay? And so I mean that integration from 15 to the infinity, I'm sorry, not 8, infinity, okay, 1 over x squared dx is equal to 1 over 15, and the integration from 16 to the infinity, that's the n, and then the other one, the n plus 1 to infinity, right? 1 over x squared dx, which is 1 over 16, and plugging this into the fourth inequality, and which was the here, the red one, I think, right? This is the fourth inequality. We will plug them into the fourth one. So it will give us 1.580440283 plus 1 over 16 less than or equal to s less than or equal to 1.580440283 plus 1 over 15. And when you find the summation, you will absolutely find the 1.64, okay, 2940283 less than or equal to s less than or equal to 1.647106950. Both the upper and lower bound are now very close to actual value, really. And if we take the average of the two, get the following estimate of the value, okay? So that the S approximately equals to 1.645023616.5. And that's a pretty darn close to actual value. The actual value was 1.64493, and it was the 1.64502, like that. It's actually close to the real value. So that we can use the integral test to estimate the value of a series, and let's move on to the next test, which is the comparison test. And in this case, unlike with the integral test, we may or may not to be able to get an idea of how good a particular partial sums will be as an estimate of the exact value of the series. And much of this will depend on how the comparison test is used. First, let's remind ourselves on how the comparison test actually works. Given a series AN, and let's assume that we've used the comparison test to show that that's a convergent. Therefore, we found the second series, which was the Bn, the convergent, and the An is less than or equal to Bn for all n values. And what we want to do is determine how good a job a partial sums again. I mean that if Sn equals to I starts from 1 to the n, this is the partial sums of Ai, okay? We'll do in estimating the actual value of the series An. Okay, this is, we are just estimating summation of An. Okay, to estimate this series, and let's actually write down the remainder for both series. Okay, and we got two different series, and the remainder will be, for example, Rn for An. Okay, this is the remainder, and the I starts from n plus 1, and the Tn, which is for B series, okay, and it is the Bi. I starts from n plus 1 to the infinity. This is comparison test because of they will use the Bn series too. So we also know that remainder of A series will less than or equal to for the remainder for Bn. When using the comparison test, it is often the case that the Bn are fairly nice terms and that we might actually be able to get an idea of the size of the Tn. For instance, if our second series is a P series, we can use the results from above to get an upper bound for the Tn as follows. I mean that the Rn less than or equal to Tn is less than or equal to integration from n plus 1 to the infinity g of x dx, okay, where g of n equals to Bn. Now example again. Using n equals to 15 to estimate the value of two to the power of n over 4 to the power of n plus 1, and starts from 0 to infinity. My friends, to do this we will first need to go through the comparison test so we can get the second series. We need now second series, okay? And to obtain the second series, okay, we'll just add and subtract from the numerator and the denominator part of the rational fraction, okay? And when you remove 1, you will obtain 2 to the power of n over 4 to the power of n, so it's equal to 1 over 2 to the power of n. We know that, my friends, this can be Bn series and also, okay? And we know that the n starts from 0 to the infinity, okay? 1 over 2 to the power of n is a geometric series and converges because we know that absolute value of r is, which is 1 over 2 less than 1. So we have gotten our second series, then let's get the estimate of that, so it will be easy. S15 equals to, okay, now we are talking about the first series, and 0 to the 15, okay, and it was the 2 to the power of n over 4 to the power of n plus 1, okay, is equal to 1.383062486, okay, this is the estimation. So how good is it? Well, we know that the R15 is less than or equal to T15, which is for the Bn, okay, and it equals to and 16 to the infinity 1 over 2 to the power of n. Okay, we know that. Now we can easily obtain the n equals to 0 to the infinity exact value, but now we are talking about the T15, which is n starts from 16 to the infinity. So we can subtract the first 15 terms from the total summation. Okay, I mean that the equals to 15 plus to the infinity. Okay, and the question part is this one, because of this is, okay. As you see. Now 16 to the infinity 1 over 2 to the power of n, it equals to n starts from 0 to the infinity 1 over 2 to the power of n minus n starts from 0 to the 15 1 over 2 to the power of n, and we know that this part is 1 over 1 minus 1 over 2, and the second part will be 1.999969482. Okay, so that's equal to 0.0000 30518. Okay, so according to this, if we use the S equals to 1.38306248, okay, so as an estimate of the actual value will be off from the exact value by no more than the 0.000 the value. Okay, it's not too bad. I mean that in this case we can write the summation n starts from 0 to the infinity 2 to the power of n over 4n plus 1 equal to 1.38306. I'm sorry, the 093004, and we can see the actual error in our estimation. After that we can write the error equals to actual value minus estimate, so that the 1.383 093004 minus 1.383062486, so it's equal to, error will be 0.00003, which is this value 05018. This is the error for this value. Okay. Now, estimation of a series will be like that, okay, my friends, and I think this will be enough